Welcome to Deep Thinkers. Somewhere inside your body, right now, as you settle into the quiet and let the weight of the day begin to leave you, there is a molecule doing its slow and patient work. It is called cholesterol. You have heard the word before, probably in the context of things you are told to worry about, but tonight I want you to think of it differently. Tonight I want you to think of it as a kind of signature, a chemical fingerprint that living animals leave behind, a molecule of fat that your body makes in enormous quantities and that bacteria and algae and fungi do not. It is, in a strange and quiet way, one of the marks of being an animal at all. And that same molecule, that same fat that runs through your blood tonight, as you lie here, was found trapped inside a stone for 558 million years. Not a fossil bone, not a shell, not an imprint you could point to and name. A smear of ancient fat, preserved as a whisper of a chemical, extracted from a thin, dark film pressed into rock on the shore of a cold sea in the far north of Russia. And that whisper, that faint chemical echo of an animal that died before there were forests, before there were fish, before there was anything you would recognize as a creature at all, is what finally proved that one of the strangest things ever to have lived on this planet was, in fact, alive, truly alive. An animal, like you. Hold that thought gently and let it carry you back. Let it carry you back past every war and every empire, past the first cities and the first fields, past the ice ages that shaped the faces of the continents, past the mammoths and the great cats, past the dinosaurs and the long ages of reptiles before them, past the first creatures that ever crawled out of the water onto land, past the trilobites, past the strange armoured things of the Cambrian seas. Keep going. Keep sinking. Go so far back that the sky itself would look wrong to you, the days shorter, the moon closer, the air thin and unfamiliar. Go back more than 500 million years, to a time so remote that the very shape of the world would be a stranger to you, when the continents you know had not yet gathered into the forms they hold today, when the land was bare rock and dust, and nothing green had ever grown upon it. Go back to a shallow, silent sea, warm in places and cold in others, its floor carpeted in a soft and living skin. And there, in that quiet water, under a sun that had only just begun to warm a planet emerging from the deepest freeze it has ever known, you would find a world unlike any that has existed before or since. Scientists have given that world a name, and it is one of the most beautiful names in all of geology. They call it the Garden of Ediacara. The paleontologist Mark McMenamin coined that phrase, and it has stuck because it captures something true and something tender about the place. A garden. Not a battlefield, not a hunting ground, a garden. Because in this world, in this long, strange, gentle chapter of the Earth's story, there were no teeth, there were no jaws, there were no claws, no stingers, no fangs, no eyes scanning the water for prey. Nothing chased anything, nothing fled, nothing was eaten alive. For what may be the last time in the entire history of our planet, there was a living world in which no creature could bite another. And I want to sit with you inside that world tonight, slowly, patiently, for a long while, and simply wander through its quiet. So before we go any deeper, let me ask you something in the way I like to ask at the start of these journeys. Tell me, wherever you are, whatever hour it happens to be where you are lying, where in the world are you listening from tonight? I always find it a comfort to imagine the many places these words travel to, the different windows and the different darknesses, all of us drifting toward the same slow sleep. If you feel like sharing, the comment is there for you, and I do read them. And if you are new here, if you have only just found this quiet corner, you are welcome to stay. Subscribe if you would like more of these slow journeys into the deep and the forgotten. There is no rush about any of it. There is no rush about anything tonight. Because that is the promise I want to make you, and I want to make it plainly so you can let go of any worry that you might miss something. This is not a story you have to stay awake for. This is not a story with a jolt in it or a twist that will snap you back from the edge of sleep. There will be no loud moment, no sudden fright. This is a slow descent, a gentle walking down into a lost world, and you are allowed to fall asleep anywhere along the way. You are allowed to drift off in the middle of a sentence and wake, if you wake at all, to find yourself somewhere deeper in the dark and the quiet. You will not lose the thread, because the thread is only this, a peaceful, ancient world, and the tender mystery of how we came to know it was real. Let the deep thoughts settle, and let yourself sink toward them slowly. There is nowhere you need to be but here. Now, let me set the scene properly, the way you would light the lamps in a room before you tell a long story. The time we are visiting has a name, given to it only recently, in the scale of these things. It is called the Ediacaran Period, and it is the very last period of an immense and ancient stretch of time called the Proterozoic Eon, the long age of early life before the world grew complicated. The Ediacaran period runs, in round numbers, from about 635 million years ago to about 538 million years ago. That is nearly 100 million years of history, an almost unimaginable span, longer than the entire age of the dinosaurs from first to last, and for most of that time, this gentle, mouthless, predator-free world simply existed, quietly, on the floor of shallow seas across a planet that would look alien to any of us. For a long while, this period did not even have this name. In the older scientific literature, particularly the Russian literature, this same slice of time was called the Vendian, and you will still find that word in the older books, a quieter and more forgotten name for the same lost age. But the name that has come to stay is Ediacaran, and it comes from a place, a real place you could stand in today if you chose to. And I find there is something soothing in that, in knowing that a chapter of Earth's deepest history is named after a set of low ancient hills you could walk across on an ordinary afternoon. Those hills are called the Ediacara Hills, and they lie in the Flinders Ranges, in the dry, red, open country of South Australia. It is a landscape of long horizons and old worn stone, the kind of place where the rocks themselves seem to have settled into a great and dignified age, and it was there, in those hills, that the first traces of this vanished world were found in a form that people could hold in their hands. The whole period takes its name from that one range of hills, from that one dry corner of Australia where the rock happened to remember what almost everywhere else forgot. And there is a fittingness to that, because so much of this story is about places where the earth, against all odds, kept a record of something it had no business keeping, soft, boneless, delicate things that should have rotted away into nothing, somehow held in stone for over 500 million years. I want you to understand just how remarkable that is, because it will matter for everything that follows. The creatures we are going to meet had no bones, they had no shells, they had no hard parts of any kind, not at first. They were soft, in some cases barely thicker than a sheet of paper, quilted and ribbed and frond, like and strange. And soft things do not fossilize. When a soft thing dies, it decays, and it is gone, and it leaves nothing behind. The reason we have any fossils at all of most of Earth's history is that hard parts, bones, teeth, shells, resist decay long enough to be buried and turned to stone. But the Ediacaran world had almost none of those hard parts. It was, for the most part, a world made entirely of soft bodies, and so the fact that we can hold any trace of it at all, that we can stand in the Flinders Ranges or on a cliff in Newfoundland or on a cold Russian shore and see the shapes of these creatures pressed into the rock, is itself a small miracle of preservation, one we will come to understand in time. For now, simply hold the wonder of it, a whole world of soft, gentle things that should have vanished without a trace, and yet did not. To reach that world, though, we have to pass through something first. We have to pass through the ice. Because the Ediacaran period does not begin in warmth and gentleness. It begins in the aftermath of catastrophe, in the slow thaw at the end of one of the most severe ice ages this planet has ever endured. Just before the Ediacaran began, the Earth went through a deep freeze that scientists call the Minoan glaciation, and it was so extreme, so total, that it has earned the name Snowball Earth. Picture that, gently, from your warm bed. A planet turned almost entirely to ice, not just the poles, not just the high latitudes, but ice reaching down, in one leading view, all the way toward the tropics, toward the equator itself, glaciers grinding across land that now sits under warm sun. The oceans capped and frozen over vast stretches. A white world, a silent world, wrapped in ice for millions of years, so cold and so still that for a long time it must have seemed as though the great experiment of life on Earth might simply be over, frozen into permanent quiet. And yet it was not over. Life endured somewhere, in refuges we can only partly imagine, clinging on through the long cold. And when the ice finally began to melt, when the planet at last warmed and the great white shell began to break apart, and the seas returned to open water, something extraordinary happened in the aftermath. The Ediacaran period opens in exactly that moment of thaw. In the immediate wake of the Minoan snowball, and it is as though the world, having come so close to ending, bloomed, the base of the Ediacaran, the very line that geologists draw to mark where this period begins, is not marked by a fossil at all. It is marked by a layer of rock, a distinctive band called a cap carbonate, a blanket of pale stone that settled over the debris left behind by the melting glaciers, a chemical signature of a world coming out of the ice. And the single global reference point for that boundary, the spot geologists chose to anchor the whole beginning of the period, lies at a place called Enorama Creek, back in the Flinders Ranges of South Australia. There is a real marker there, a golden spike, as geologists like to call it, driven into the rock to say, here, at this exact layer, one age ended and another began. In the year 2004, the International Union of Geological Sciences formally ratified all of this and gave the Ediacaran its official place on the timescale, the first entirely new geological period to be added in around 120 years. But I offer that only as a quiet aside, a small human footnote to a vastly older story. Because the real event is not the ratification. The real event is the bloom itself, a frozen world, thawing and life stirring in the meltwater. So let us go down now, past the cap carbonate, past the memory of the ice, into the warm and shallow sea that spread across the recovering world. Let your breathing slow, and let us descend together onto the seafloor of the early Ediacaran and stand there quietly and look at what covered it. The first thing you would notice if you could stand on that ancient seafloor is that it was not bare. It was not clean sand or empty mud. It was covered, carpeted, in a soft, living skin. Scientists call these carpets microbial mats or mat grounds, and they were the foundation of this entire world, the ground beneath everything, the living floor of the garden. Imagine a leathery, rubbery, slightly sticky film spread across the sediment as far as you could see, made of countless microscopic bacteria, all living together in dense layers, a skin of life laid over the bones of the seabed. In some places it might have been slick and glistening, in others wrinkled and textured and tough. It was alive, all of it, a single continuous living surface stretching across the shallow seafloor of the world, and this mat, this quiet green-brown skin of bacteria, was not merely scenery. It was the ground the Ediacaran creatures lived on, and around and against. It was the surface they anchored to, the surface they lay upon, and, as we will come to see, for at least some of them, it was the very thing they fed upon. The whole gentle economy of this world rested on those mats. They were the pasture of a world with no grazers, the field before there was any appetite to harvest it. And across that living carpet, in the quiet, sunlit shallows and in the darker, deeper waters below, grew the strangest garden the earth has ever known. I say garden, and I keep saying garden, and I want you to understand that this is not only a poetic flourish, it is, in a real sense, how these creatures lived. They did not hunt. They did not chase. Most of them did not move at all, or moved so slowly and so rarely that they might as well have been rooted. They stood or lay or spread themselves across the mats, and they took in what they needed from the water and the surface around them, quietly, without violence, the way a plant takes in sunlight and rain. But here is the strange and important thing, the thing that will sit at the heart of everything we explore together. They were not plants. Many of them, we now believe, were animals, soft, still, silent animals, living a life so unlike the frantic, hungry, biting lives of the animals that came after them, that for decades scientists could barely agree on what they were at all, whether they were animals or fungi or lichens, or vast single living cells, or something else entirely, some separate experiment in being alive that has no name in our world because nothing like it survived. Let me hold one of them up for you now, gently, the way you might lift a pressed flower from between the pages of an old book, and let you look at it in the lamplight before we go any further. Its name is Dickinsonia, and it may be the strangest animal you will ever be introduced to. Picture an oval, a flat, ribbed oval, lying on the living mat like something dropped and forgotten. Some of them were only a few millimeters across, small enough to rest on a fingertip, but others grew astonishingly large, over 1.5 meters in length, longer than your outstretched arm. Longer than a person is tall in some cases, and yet, for all that length, it was almost nothing in thickness. Only millimeters thick, thinner than a coin. Imagine a quilted mat, a bath mat, a soft ribbed thing spread out across the seafloor, wider than a doormat and thinner than a slice of bread, patterned all over with fine ribs running out from a central line down its length. That was Dickinsonia, a living quilt, a breathing mat. Lying flat against the microbial carpet, taking in its meals, we now believe, directly through its skin, absorbing the nutrients of the world into its body across its whole broad surface without ever needing to take a bite of anything, because it had nothing to bite with. And there is a detail about its body, a small and beautiful detail that I want to give you because it captures how genuinely alien this world was. The ribs of Dickinsonia, running out on either side of that central midline, do not match up the way you might expect. If you look at your own body, or the body of almost any animal alive today, you find mirror symmetry. The left side is a reflection of the right, your left hand a mirror of your right hand, each rib matched by its partner across the middle. But Dickinsonia's ribs are offset. The rib on the left does not line up with the rib on the right. Instead, each one is shifted, staggered, so that they interlock along the midline rather than mirroring each other. Scientists call this glide reflection symmetry or glide symmetry, and the reason it is worth pausing on is that it is a body plan with no exact equal among any animal alive on Earth today. Nothing living is built quite like this. It is a design from a lost drafting table, a way of being an animal that the world tried once, long ago, in the quiet of the Ediacaran, and never quite tried again. When you picture Dickinsonia, picture that, a soft-ribbed oval whose two sides do not mirror but glide past one another, a symmetry that vanished from the world and never returned. And it grew, as living things grow, but it grew in its own particular way. Dickinsonia added new ribs, the scientists call them modules or isomers, at one end of its body, at a growth pole, laying down segment after segment as it aged, so that the older and larger individuals carried more ribs than the young ones did. You could, in a sense, read its age in its body, the way you can read the age of a tree in its rings. A small Dickinsonia was a young Dickinsonia with few segments. A great metre-long one was an old individual that had spent a long, slow life, adding rib after rib after rib at its growing end, while it lay upon the mats and drank the sea. There is something deeply peaceful in that image, I think. A life spent lying still on a living carpet under shallow water, slowly, patiently lengthening, one soft segment at a time, in a world with nothing to fear. But I have gotten ahead of myself, because I have told you these things as though we have always known them, and we have not. For a very long time, we did not know any of this. For a very long time, Dickinsonia was one of the great riddles of paleontology, and the argument over what it even was, animal, fungus, lichen, or giant single cell, went on and on, decade after decade, without resolution. The creatures of the Ediacaran were found long before anyone could say with confidence whether they were looking at the remains of animals at all. And that is really where the human part of our story begins, not with the ancient creatures themselves, but with the people who first stumbled upon their traces in the rock and dared to wonder whether they might be looking at something impossibly old. That story begins, in one telling, in the year 1946, in those same Ediacara hills of the Flinders Ranges that would eventually give the whole period its name. A geologist named Reg Sprigg was out in that dry, red country, working among abandoned mines, surveying old workings in the ancient hills. He was not looking for the dawn of animal life. Almost no one at that time believed there was any complex life to be found in rocks that old, the settled wisdom of the day, held that complex living things simply did not exist before the Cambrian. That the deep Precambrian rocks were essentially empty of such fossils, barren of anything but the simplest microscopic life. But Sprigg, turning over the ancient stone in those hills, found impressions in it, Soft, strange, disc-like and frond-like shapes pressed into the old rock, the ghostly outlines of creatures no one could name. He recognized that he had found something, and he said so. And for years, the significance of what he had found was doubted. The idea that these impressions could be older than the Cambrian, that they could be genuine traces of complex life from a time when complex life was not supposed to exist, was too much for the science of the day to easily accept. His discovery lingered in a kind of uncertainty, its true age and importance argued over, not yet allowed into the story of life. And so the door that Reg Sprigg had pushed against did not truly swing open in Australia. It swung open, instead, on the other side of the world, in England, in a forest, and it was opened, remarkably, by children. There is a place in the English Midlands called Charnwood Forest, an area of very old rock, and it was there, in the 1950s, that a schoolgirl named Tina Negus, out among the ancient stones, noticed something pressed into the rock. It was a shape like a frond, like a feather, like a leaf of some plant, imprinted in stone that everyone knew was extremely old, far older than the Cambrian, far older than any rock that was supposed to hold such a thing. She saw it. She recognized that it was strange and that it mattered. And when she brought it to the attention of a teacher, she was dismissed. She was told, in effect, that it could not be what it appeared to be, because there were no fossils in rock that old. Everyone knew that. The frond in the ancient stone was, according to the settled wisdom, an impossibility, and so a girl who had seen an impossibility with her own eyes was told, gently or not, that she was mistaken. But the frond was still there in the rock, and the rock did not care what the settled wisdom said. Not long after, another young person, a schoolboy named Roger Mason, came upon the same kind of impression in Charnwood Forest, and in 1957 the find was reported and taken seriously. And this time the door came off its hinges, because the rock at Charnwood Forest was, beyond any argument, older than the Cambrian. There was no wiggle room, no way to explain it away as a younger fossil that had somehow ended up in older stone. Here was a complex, frond-shaped organism unmistakably preserved in rock that was unmistakably Precambrian. The dogma, the flat and confident belief that no complex life existed before the Cambrian, simply shattered. This fossil, this frond found by children in an English forest, became the first widely accepted example of complex life from before the Cambrian. It was given a name, Charnia masoni, after Charnwood Forest where it was found, and after Roger Mason who reported it, and it stands to this day as one of the most important fossils ever discovered, the one that broke a false certainty and opened the door to a whole lost world. And Charnia carries its own quiet paradox, one that will become one of the threads we follow down into sleep tonight. Charnia was frond-shaped, feather-shaped, and to look at it you might well think of a modern sea pen, one of those soft, feathery creatures that stand up from the seafloor in gardens of the deep ocean today. But here is the strange thing about Charnia, the thing that has puzzled scientists, and that I want to leave with you now, unanswered, to carry with you as you drift. Charnia lived in deep water. It lived below the sunlit zone, down where the sunlight does not reach, in the darkness of the deeper sea. And that means, think about this slowly, that Charnia could not have fed on sunlight. It could not have been a plant, could not have photosynthesized, could not have made its living the way a leaf does, because there was no light where it lived. A frond, shaped like a feather, standing in the dark. So how did it feed? How does a delicate, feathery, rooted-looking thing, standing in water too deep and too dark for any sunlight ever to reach it, take in enough to live and grow? What could it possibly have been eating, down there in the lightless quiet, with no mouth that anyone could find, and no sun to drink? Hold that question. Do not strain after the answer. I promise you the answer will come, further along in our slow descent. And it is a gentle and beautiful answer. But hold the question the way you might hold a small stone in your palm, feeling its shape, letting it be. A frond in the dark, feeding on something we could not at first imagine. That is the kind of quiet riddle that this whole world is made of, and we have all the time in the night to sit with it, because that, in the end, is what the Garden of Ediacara offers us. Not a single tidy answer, but a slow accumulation of gentle mysteries, each one grounded in real rock, real places, real fossils you could hold, the dry hills of Australia, the ancient forest of England, the cold shores of the northern sea, and each one deepening the wonder rather than dissolving it. A world that came out of the ice and bloomed, a seafloor carpeted in living skin. Soft, ribbed, quilted creatures lying still upon it, taking in the world through their surfaces, growing slowly, fearing nothing. Because there was nothing yet in all the world that could hurt them. No teeth, no jaws, no hunt. And, waiting for us further down in the dark, the astonishing human story of how we finally proved that these silent quilted things were not plants, not fungi, not mere patterns in the mud, but true animals, proved it with a molecule of fat. The very same fat that moves through your own body as you lie here now, quietly breathing, quietly sinking towards sleep. So let us keep going down. Let us walk a little further into the garden together, into that shallow, sunlit, silent sea, and meet more of the strange and gentle things that grew there, and slowly, gently, come to understand how such a world could live, and how we ever came to know it. It begins, the way so many of the best discoveries begin, not with a grand expedition or a well-funded laboratory or a team of scholars who already knew what they were looking for, but with a geologist walking alone across dry and sun-bleached ground in the hills of South Australia in a summer year after a long and exhausting war, doing the ordinary administrative work of surveying abandoned mines that nobody was operating anymore. His name was Reg Sprigg. The year was 1946. The hills around him were the Ediacara Hills, which form part of the Flinders Ranges, a long spine of ancient and eroded rock running north through the interior of South Australia, a place of red dust and sharp light, of eucalyptus and silence, of geological time written so plainly in the exposed stone that even a casual observer might feel, standing there in the heat, that the ground beneath their feet is not quite ordinary ground. Sprigg was there to assess whether any of the old mines were worth reopening. What he found instead, lying on the surface of the pale sandstone, half revealed by the angle of the afternoon light, pressed into rock that geologists at the time believed to be the oldest and simplest kind, were shapes, soft, organic shapes. Discs, fronds, quilted, forms, with a structure that was nothing like a mineral crystal, nothing like the random patterns that wind or water might press into sediment, nothing like anything the inorganic world has ever been known to produce. They looked, unmistakably, like living things, or like the shadows of living things. Shadows pressed into sandstone, thin and delicate, precise in their patterning, as though something that was once alive had lain down gently on the seafloor and refused, even after 600 million years, to entirely leave. Sprigg recognized what he was looking at as fossils, body impressions of organisms. But the problem was the age of the rock. Because geologists and paleontologists of that era operated under a working assumption, an assumption so deeply embedded in their thinking that it functioned less like a hypothesis and more like a law of nature, which said that complex life with real bodies, with structure and organization and size, did not exist before the Cambrian. The Cambrian period, which began perhaps 538 million years ago, was understood to be the beginning. Before it, nothing complex. Bacteria at most. Simple films. No bodies worth speaking of. That was the consensus, the comfortable agreement of the field, and when Sprigg looked at the shapes in the Ediacaran sandstone and saw that the rock was unambiguously older than any Cambrian deposit, the natural response from the scientific community around him was not wonder. It was skepticism. He tried to publish. He presented his findings. The fossils were real. He had seen them, photographed them, mapped them, but the age was the problem. Older than the Cambrian. And the rule said nothing complex lived before the Cambrian. And so the findings met the quiet, polite resistance that discovery so often meets when it lands before the world is ready for it, the suggestion that perhaps the age was wrong. Or the identification was wrong. Or perhaps what Sprigg had found were simply trace markings, coincidences of geology, shapes that only resembled organisms if you squinted and hoped. The significance of what he had uncovered would be doubted for years. And yet the fossils were there. They remained there, in the dry hills, patient and quiet and 500 million years old, indifferent to what the scientific community thought of them. The story might have moved very slowly indeed, might have taken many more decades to unfold, if not for a forest in England and a schoolgirl who was told she was wrong, and a schoolboy who, a few years later, turned out to be right. Charnwood Forest lies in Leicestershire, in the English Midlands. It is not a dramatic landscape, not the kind of place you would necessarily visit if you were searching for the origins of complex life on Earth. But beneath the forest, and exposed in various outcrops and rocky slopes, lie some of the oldest surface rocks in England. Precambrian rocks, rocks laid down before the Cambrian. Rocks which geologists had studied for many years, and in which, by the same ruling consensus that had met Sprigg's Australian fossils with doubt, no complex organism was supposed to exist. No fossil from the age of simple life should look like anything. It should look like nothing. Because there was nothing to look at. In 1957, a schoolgirl named Tina Negus went walking in Charnwood Forest and noticed, on the surface of an exposed slab of ancient rock, the impression of something frond-shaped. Something that looked, with a kind of uncanny clarity, like a fern or a sea pen or perhaps a leaf, but preserved in rock that was unquestionably older than the Cambrian. She told her geography teacher. Her geography teacher, reasoning within the same confident consensus that had already greeted Sprigg's findings with skepticism, told her that such a thing was impossible. There were no fossils in Precambrian rock. Whatever she had seen was not what she thought she had seen. Tina Negus was dismissed. And then, a short time later, a schoolboy named Roger Mason walked through the same forest, found what was almost certainly the same or a closely related impression, and reported it to a geologist at the University of Leicester, who recognized immediately that what Mason had found was something genuinely significant. The formal scientific description of the fossil followed in 1957, and it was named Charnia masoni, the species name honoring Roger Mason, the boy who was believed. This is not the only time in the history of science that a woman's observation was set aside and a man's identical observation was credited, and the telling of it here is not meant to be bitter, only honest, because honesty is part of the atmosphere of this particular garden, where so many things were overlooked for so long. But what Charnia masoni turned out to be, what Roger Mason's reported fossil and Tina Negus's earlier unrecorded observation and the careful work of scientists in the years that followed confirmed, was one of the most important fossils ever found on this planet. Because Charnia masoni was the discovery that shattered the consensus. It was the fossil that could not be explained away. Not because of anything dramatic about its appearance, but because of the single, undeniable, geologically verified fact of the rock it was found in. The rock at Charnwood Forest was not Cambrian. It was not even close to Cambrian. It was older, unambiguously and irreversibly older, and there was no credible way to argue otherwise. Because the Precambrian age of those English outcrops had been studied for a long time by people who knew very well what they were doing. And yet there was Charnia, complex, frond-shaped, clearly biological, in rock that the consensus said should contain nothing of the kind. That was the end of the consensus. Not immediately. Science rarely moves as a single clean break. But from Charnia masoni onward, the field could no longer hold. The scaffolding of the no-complex life before the Cambrian assumption quietly came apart, and what replaced it over the following decades was something far more interesting. The slow accumulation of evidence for a whole world, a whole period of time, full of large and structurally complex, soft-bodied organisms, alive and growing and living their strange, quiet lives on ancient seafloors before any animal had ever developed the kind of hard skeleton that tends to leave unambiguous traces in stone. This is what Reg Sprigg had been looking at in the Ediacara hills in 1946. This is what Tina Negus had noticed and been told to ignore. This is what the pale sandstone of South Australia had been trying to tell us for as long as people had been walking across it. Now, consider Charnia masoni again. Consider what it actually looked like and where it actually lived, and notice that even once its age was established and its significance accepted, there remained a second problem, a quiet, puzzling problem that has a beautiful and somewhat unexpected answer, and which serves as the first doorway into understanding how all these ancient creatures actually survived. Charnia was frond-shaped. It looked, in its overall form, like a sea pen looks today, one of those colonial organisms you sometimes see in photographs of deep ocean floors, feathery or leaf-shaped, rooted to the seafloor by a disc called a holdfast, extending upward into the water. Long, branching, structured, Charnia had a stalk, a holdfast to anchor it to the sediment, and a frond that extended above. Branching in a regular and organized way, the branches themselves branching, the whole structure displaying the kind of mathematical self-repetition that botanists would recognize in ferns and that mathematicians would later describe as fractal, the same pattern repeated at smaller and smaller scales. But here is the problem. The rock in which Charnia was found at Charnwood Forest, and many of the rocks in which similar fronds are found at the deep-water Ediacaran sites, tell us something important about where these organisms lived. They tell us, from the evidence of the sediments around them, from the layers of material laid down above and below them, from the way the stone records the water depth and the light conditions of the ancient seafloor, that Charnia and its relatives lived in deep water. Water too deep for sunlight to reach. Think about what that means for a moment. We are accustomed, in the modern world, to dividing life on Earth into rough categories based on where the energy comes from. Plants and algae and photosynthetic bacteria use sunlight. Animals eat plants, or eat other animals, or find other ways to harvest energy that ultimately traces back to the sun. Life, as we generally understand it, is driven by light, either directly or at one remove. And so when you encounter a large, apparently complex organism, a frond over a foot long, with a structured branching body, anchored to a seafloor and presumably doing something metabolically active up there in the water, the natural first assumption is that it must be harvesting sunlight. That is what fronds are for. That is the obvious explanation. Except that Charnia lived where the sunlight did not reach, below the sunlit zone, below the depth at which enough light penetrates the water to power photosynthesis. There is no sunlit energy source to harvest. Whatever Charnia was doing, whatever metabolic strategy allowed this structured, growing, anchored frond to persist and to thrive on an ancient deep seafloor, it was not photosynthesis. And this is where the question opens, gently and persistently, like a door swinging inward in a dark hall. How, then, did it feed? We will come back to that question. We will sit with it for a while, because the answer is one of the most revealing things about the entire Ediacaran world, about what made these organisms so strange, and why the world they built was structured so differently from any world that has existed since. But first, let us stay a moment longer with the story of how this period came to be recognized, and with the tools that scientists use to mark the boundaries of deep time. The period itself, the Ediacaran, was not officially a period for most of the time that geologists were studying it. For many decades, the rocks and the fossils they contained existed in a kind of nominal limbo, acknowledged, studied, increasingly well documented, but not formally assigned to a named interval of geological time. In Russia, where many important Ediacaran fossils were found along the White Sea coast, the period was known as the Vendian, and that name appears in older literature. In 2004, the International Union of Geological Sciences formally ratified the Ediacaran Period, an event that may seem, from the outside, like a purely administrative matter, but which represented something meaningful. It was the first entirely new geological period to be added to the official timescale in approximately 120 years. The field was acknowledging, formally and on record, that what existed in these rocks deserved its own chapter. The pre-Cambrian was not simply featureless. It was a world. The base of the Ediacaran period is defined in an unusual way. Most geological period boundaries are defined by fossils, by the first appearance or disappearance of particular organisms. The base of the Ediacaran is instead defined by a chemical and mineralogical feature, a layer of rock called a cap carbonate. This is a layer of carbonate minerals, essentially limestone, that blankets the glacial deposits left behind by the Marinoan glaciation, the great snowball Earth event that, roughly 635 million years ago, may have covered the planet from pole to pole in ice. When the ice finally melted, when the climate swung violently back from frozen to warm in a way that is still not entirely understood, it left behind a distinctive signature in the rock record, a sudden, specific chemical layer that can be recognized in ancient rocks on multiple continents. That layer is the beginning of the Ediacaran. The official global reference point for that boundary, what geologists call the golden spike, or the global boundary stratotype section and point, the GSSP. is a specific outcrop at a place called Enorama Creek in the Flinders Ranges of South Australia. Not far, as it happens, from the hills where Reg Sprigg walked in 1946 and found the first soft impressions in the pale stone. There is something fitting about that. The name of the period comes from the hills. The defined beginning of the period is anchored in the same region, in a creek bed where the boundary between the glacial past and the Ediacaran future is visible in the exposed layering of the rock, precise and datable and real. And the garden that bloomed after the ice, the garden that we have been slowly entering since the beginning of this night, bloomed from that boundary outward, across a cooling ocean, onto a seafloor that had been scraped nearly clean and was now repopulated gradually, and then, with what the fossil record suggests, was increasing complexity and diversity by organisms unlike anything that had come before or, in some ways, has come since. Which brings us to Dickinsonia. If Charnia masoni is the fossil that broke the consensus, Dickinsonia is the fossil that most defines the character of the Ediacaran in the popular imagination, and in the scientific one, too, it is Dickinsonia that has been studied most intensively over the longest period of time. Dickinsonia about which the debates have been most sustained and most pointed, and Dickinsonia that yielded, in 2018, the piece of molecular evidence that finally settled the deepest question of all about what these organisms actually were. We will come to that evidence in time. For now, let us simply meet it. Imagine a mat, an oval mat or a roughly elliptical shape lying flat on the seafloor. It has a midline running along its longest axis, like the spine of a leaf, and from either side of that midline, ribs extend outward, many ribs, close set, parallel like the ribbing of a quilted blanket, or the pattern of a bath mat, or the even parallel folds you sometimes see in the skin of a slow-moving mudflat creature. The organism is flat, not just slightly flattened, the way a flounder is flat, retaining real three-dimensional depth, but genuinely, almost improbably thin. Millimeters thick, in many cases, despite being, in the largest known specimens, more than 1.5 meters across. Over 1.4 meters at its greatest. No thicker, in some specimens, than a coin you might hold between 2 fingers. And yet clearly it grew. Clearly it had internal structure. Clearly it was organized in a biological way, not a random one. The ribbed segments, which paleontologists call modules or isomers, are arranged with a particular, very specific geometry that has attracted enormous scientific attention. The ribs on one side of the midline are not mirror images of the ribs on the other side. They are offset. Each rib begins slightly further along the midline than the corresponding rib on the opposite side, a pattern called glide reflection symmetry, which is a term from crystallography that describes a kind of symmetry where a shape is reflected and then shifted slightly along an axis. You can find glide reflection symmetry in the patterns of footprints left by a walking animal, the left foot, then the right foot, each offset from the other down the trail. You can find it in the teeth of a zipper. You find it, notably, in almost nothing alive today. No modern animal body plan is organized in precisely this way. Dickinsonia's geometry is its own thing, something that evolution arrived at once, 500 million years ago, and then, as far as we can tell, never arrived at again. It grew by adding new modules at one end. One pole of the oval body was the growth pole, the end where new segments appeared and where the organism expanded. Larger specimens have more segments. Older individuals have more ribs. This means that if you find a population of Dickinsonia fossils at a single site, You can, in principle, reconstruct the organism's growth trajectory simply by counting ribs. A smaller specimen with fewer segments is younger, a larger specimen with more segments is older, and the progression from one to the other tells you something about how growth proceeded, at what rate, and in what pattern. This is a kind of biological information that is extraordinarily rare in fossils this ancient. Most Precambrian organisms left us no such record. Dickinsonia left us something close to a growth chart, a biological ledger stretching across 500 million years of stillness in the rock. It lived on the seafloor. Almost certainly it lay flat against the microbial mat, that living carpet of bacteria that covered the ancient seafloor the way moss covers a stone in a damp garden. The mat was not a background detail, it was not scenery. It was, in a very real sense, the world that Dickinsonia and its contemporaries were built for, and the world that many of them were, in some capacity, feeding from, though the precise mechanism of that feeding. And whether Dickinsonia truly ate in any sense we would recognize is something we will need to examine carefully, because it is one of the stranger and more beautiful aspects of this ancient world. But let us stay a moment longer with the shape of the animal, the organism, whatever we call it, whose name we will be able to speak with rather more confidence by the time this night has unfolded further. The flat, quilted oval, the glide, symmetric ribs, the growth pole adding segment after segment as the individual aged, the astonishing thinness relative to the breadth. If you were to try to imagine what touching Dickinsonia might have felt like, and there is no harm in that imagining, in feeling your way towards something 500 million years gone, it would perhaps have felt something like a very large, very soft, very slightly textured piece of membrane, something between a jellyfish and a deflated inner tube. Something with just enough structural coherence to hold its shape against the mild currents of the Ediacaran Sea, but without the rigid skeleton, the mineralized shell, the hard internal framework that we associate so readily with animals in our own experience. No bones, no shell, no teeth, no eyes as far as anyone has been able to determine, no mouth that has left any trace in the fossil record. No gut, no obvious way in or out for any food that might have entered. And this is where the question that Charnia opened, the question about feeding in the dark, in the depths, without sunlight, becomes the question that the whole Ediacaran world is really asking. Not just for Charnia, not just for one odd frond in a Leicestershire forest or on a South Australian hillside, but for Dickinsonia, for the hundreds of other species that lived alongside it, for a seafloor full of organisms, soft and quilted and mouthless and still, that nonetheless persisted and grew and spread and diversified across tens of millions of years. A whole world of living things that apparently ate without mouths, digested without guts, and fed, in some way we are only now beginning to properly understand, on the ancient living skin of the sea. That question, if nothing had a mouth, what did anything eat, is the central mystery of the Ediacaran garden. And the answer to it, which is stranger and more interesting than a simple they were plants, or they photosynthesize, or even they were just bacteria after all, begins with that living carpet on the seafloor, and with what happens when you lay a flat, ribbed, high surface area body directly on top of it and wait. But we are getting ahead of ourselves, just slightly. The garden is still coming into view, the organisms are still being introduced one by one as the night deepens and the story settles. And there is one more piece of context that belongs here, one more quiet aside about the difficulty of reading this ancient world and the tools we use to do it. Before we walk further into the mat grounds and begin to understand the feeding and the living and the dying of the things that grew there. The fossils themselves, the impressions in the sandstone, the cast shapes, the faint ribbed shadows that Reg Sprigg found in the afternoon light, and Tina Negus and Roger Mason found in the Charnwood Forest, and that hundreds of paleontologists have found since on every continent where ancient Precambrian rock is exposed, are not normal fossils. They are not the kind of fossil that most people picture when they think of paleontology. Most familiar fossils are hard parts, bones, teeth, shells, things that were already mineralized in life, and that persisted because mineralization is durable. The organisms of the Ediacaran had no hard parts. They were almost entirely soft. And soft things do not, under ordinary circumstances, fossilize, they decay. They are eaten by bacteria. They dissolve. They vanish without a trace, leaving the rock as clean and empty as if they had never been there at all. The reason Ediacaran fossils exist, the reason we have anything to look at, is a combination of circumstances that was, in geological terms, relatively unusual, and that scientists have given a name. They call it Ediacara-style preservation. And the mechanism involves, in many cases, the very same microbial mats that the organisms lived on. When an Ediacaran organism died on the seafloor, its body lay on, or in the mat. As it began to decompose, the bacterial activity around it could, under the right geochemical conditions, trigger the rapid precipitation of minerals from the water above, particularly a mineral called pyrite. Iron sulfide, the same mineral sometimes called fool's gold. These mineral films precipitated quickly enough, in some cases, to capture the shape of the decaying body before that shape was lost entirely. They formed a kind of mould around the organism, a chemical cast, a death mask, and the sediment that accumulated above and around this process, over time, compressed and lithified into the sandstone that holds the impressions we study today. The name is apt. A death mask. A thin mineral replica of something that was once alive and soft, lying quiet in the seafloor sediment, preserved not by the strength of its own material, but by the chemistry of its dying, and by the bacterial life that surrounded it even as it went. There is something quiet and strange about that preservation mode, the idea that the mats that these organisms lived on also, in death, helped to record their shapes, that the living skin of the ancient seafloor served as both the food source and the fossil maker of the creatures that rested on it. And so we have these impressions. These quiet, precise, ribbed shadows in the pale sandstone of the Ediacara hills, the frond shape of Charnia in the grey Precambrian rock of Charnwood Forest, the ovals and discs and branching forms that continued to be found once the field opened up at site after site around the world, in Russia, in Canada, in Namibia, in the Arctic, on the cold exposed shores of the Northern Sea. Dickinsonia among them, flat, ribbed, asymmetrically patterned, growing steadily from one end, and for a very long time in the scientific literature, almost impossible to categorically identify as any particular kind of living thing. Because this is the other question that Dickinsonia posed, the other loop that ran, open and unanswered. For decades through the literature and the debates and the papers and the conferences. Not just how did these organisms live, but what were they? Were they animals? Were they fungi? Were they giant single-celled organisms, protists, technically, or amoeba-like things, but scaled up to 1.5 meters? Were they something entirely separate from any lineage of life we have a name for? A failed experiment in multicellularity, a branch of the tree of life that grew and then went extinct and left no descendants at all? Adolf Seelacher, a German paleontologist of enormous influence and careful thinking, proposed in the late 20th century that many Ediacaran organisms, including Dickinsonia, belonged to a group he called the Vendobionta. The Vendobionta, in Seelacher's formulation, were not animals and not fungi and not plants. They were a separate kind of multicellular life altogether, built from quilted compartments, filled with fluid or gel, something like the internal structure of an air mattress or a water balloon in microscopic repetition, and organized in body plans, including the glide-symmetric ribbed plan of Dickinsonia, that have no equivalent among any modern living lineage. The Vendobionta, by this hypothesis, were a separate invention of complex multicellular life. An experiment that ran for millions of years, produced extraordinary diversity and size, and then ended without leaving descendants. A branch that grew and stopped. This hypothesis was taken seriously. It is still taken seriously in certain forms. The body plans really are strange. The glide symmetry really is unlike anything alive today. The mouthlessness, the gutlessness, the apparent absence of internal organs of any kind, all of this is consistent with something that is not quite an animal, or not quite in the lineage that leads to animals. And yet the evidence was never conclusive in either direction for many years. The debate continued. The fossils were studied and restudied, new specimens were found, growth patterns were analyzed, chemical tests were run, phylogenetic analyses were constructed and contested, and for a long time the question of what Dickinsonia actually was remained, genuinely and frustratingly, open. Until 2018. Until a thin organic film on the surface of a Dickinsonia specimen from the White Sea coast of Russia. Until the work of Ilya Bobrovskiy and Jochen and their colleagues at the Australian National University. Until a molecule of cholesterol, 500 million years old, waiting patiently in the stone. But that is the next movement of the night. That is the payoff that the whole story of the discovery drama has been building toward, the moment when the long argument about what these organisms were finally found its answer, not in the shape of a fossil or the counting of ribs, but in chemistry, in the molecular traces that living things leave behind when their bodies break down into rock and time, and that can be extracted painstakingly from ancient stone, by people who know precisely what they are looking for and exactly what it means when they find it. For now, we are still in the discovery, still in the movement from Reg Sprigg and his abandoned mines to Roger Mason and his Charnwood Forest, to the long, slow opening of the field, to the ratification of a period, to the gradual accumulation of Dickinsonia specimens on the White Sea coast and the Ediacara hills and a dozen other ancient sites. Still standing at the edge of the garden, reading the shapes in the stone, asking the questions that the stone has held in patient silence for 600 million years. The garden is old. It is older than anything familiar. And it is patient in the way that only stone can be patient, absolutely, without effort, without intention, without the slightest concern for whether we understand it or not. It holds its quiet, ribbed impressions in the pale sandstone, and it waits, and we have been asking the right questions for just long enough now to begin. Carefully and precisely, and with a growing sense of wonder, to receive the answers. Close your eyes, if you like, and rest there for a moment in the stillness of that ancient seafloor, in the soft blue-grey light of Ediacaran water, very deep, very calm. No sound, no movement from the surface, too far above to reach, just the quiet carpet of the mats. and the slow-ribbed ovals of Dickinsonia resting against them, and the frond-shaped forms of Charnia lifting gently in whatever mild current moved through that sunless deep. Growing, absorbing, knowing nothing about teeth, because there were no teeth, knowing nothing about fear, because there was nothing yet that warranted it, nothing in all the world, in that long, quiet chapter before the Cambrian, that could bite. And so we remain here, in this ancient stillness, with the questions that have gathered slowly over the course of a long scientific century. And now, at last, we can begin to answer some of them. Not all. The garden does not surrender everything. But enough. Enough to understand, in something approaching real detail, how this world actually worked. How life managed to live here for tens of millions of years without a single mouth to speak of. Consider what that means for just a moment. No mouths. The phrase is simple enough, and yet when you sit with it long enough, it begins to feel genuinely strange. The way that very familiar words sometimes do when you repeat them too many times in the dark. No mouths, no guts, no internal organs of any recognizable kind. The organisms that lived on this ancient seafloor, drifting gently in the current or resting against the microbial carpet in the sediment, did not eat in any way that a modern animal would recognize as eating. They did not hunt. They did not swallow. They had no stomach to fill, no intestine to move food through, no way of taking something in at one end and expelling the remainder at the other. The whole elegant, terrible machinery of digestion, the process that drives nearly every behavior of nearly every animal alive on Earth today, from the simplest worm to the largest whale, had not yet been invented. Or, more precisely, it was being invented. Very slowly. And the world before it was complete was a profoundly different world. The leading explanation for how these organisms sustained themselves is one that scientists call osmotrophy, which is a word that sounds technical and Latin but resolves, in practice, into something almost meditative. Osmotrophy means absorbing nutrients directly through the body surface, not swallowing food, not even touching it with a specialized organ, but simply lying against a rich medium and drawing molecules across the boundary of the skin. The way a dry sponge, pressed against a wet surface, will fill itself without any apparent effort. The way tree roots pull water from the soil without any pump you can point to, through sheer differential pressure and the patient geometry of tiny spaces. Osmotrophy is eating, by simply being in contact with something nutritious and allowing chemistry to do its slow molecular work across the boundary of the body. And the Ediacaran seafloor was, in this sense, a spectacularly good place to practice it. Because the mats were everywhere. Thick, leathery, living carpets of microbial life, cyanobacteria and other microbes growing in dense, layered sheets across the sediment surface, binding the grains together, trapping particles, building chemical gradients in the water just above them, releasing organic molecules into the water column as they grew and died and decomposed. The mats were, in a sense, the medium in which the whole garden existed. They were the substrate and the food source and the structural support all at once. An organism that could absorb nutrients across its skin, pressed against a mat like this, would not have needed a mouth. The mat would have fed it as efficiently as anything we might call a digestive system, perhaps more efficiently, given the extraordinary surface areas that some of these body plans achieved. Dickinsonia, in particular, seems beautifully suited to this mode of life. Think again of that flattened oval, those carefully offset ribs, That body plan, no thicker than a centimetre, even when it stretched to more than a metre in length. The entire organism, from edge to edge, was essentially one large absorptive surface in contact with the mat below. There was no interior to speak of, no cavity, no hollow. Just a thin, ribbed body, lying flat, with every part of it touching the microbial film beneath. The mathematics of this arrangement are striking. A modern animal of comparable length, say a medium-sized fish or a large sea cucumber, will have absorbed nutrients through a comparatively tiny surface area of gut lining deep inside its body, fed by a mouth and a passage that concentrate food into one space. Dickinsonia, by contrast, was all surface, all contact. Every square centimetre of its body was potentially drawing nutrition from the mat it rested on, without any of the intermediate steps that we regard as necessary for an animal to feed. And the evidence that this is what happened, or something close to it, lies not just in the body plan, but in the fossils themselves. Because Dickinsonia and a related organism called Yorgia did not only leave impressions of their bodies in the stone, they left something rarer and stranger and more quietly remarkable. They left what paleontologists call resting traces, patches in the microbial mat where the organism had lain, where the mat had been consumed or dissolved or altered beneath the body's weight and chemistry, and where the organism had then moved on, leaving behind a kind of ghost of itself, a negative space, a record of absence where the mat had been eaten away in exactly the outline of the creature that had rested there. Imagine finding that in a piece of stone. Imagine holding a slab of pale Ediacaran sandstone and seeing, in the same surface, two things: the impression of the organism itself, its ribs and its midline pressed into the rock with perfect clarity, and just a few centimetres away, the shadow of where it had been before, a slightly different texture in the stone, an absence where the mat had been consumed, the exact same ribbed oval shape but emptied, a mould without its cast, a resting place abandoned. And sometimes, in the same slab, a series of these traces, one after another, each slightly different in position, each showing the organism having consumed the mat beneath it and then moved, glided, perhaps, by some mechanism we cannot directly observe, to an adjacent patch of fresh mat, to rest again and feed again in that same patient, utterly unhurried way. This is, when you allow yourself to feel the weight of it, some of the oldest evidence of animal behaviour that exists anywhere in the rock record. An animal choosing, or at least following some chemical gradient, some gradient of nutrition, to move from a depleted patch to a fresh one. Not hunting, not chasing, not striking with a jaw or a claw or a sting, just sliding, slowly and perhaps continuously, across a living carpet, absorbing it from below, leaving its outline in the sediment behind it like a trail of quiet consumption. The earliest meal we can read in stone, and it was as gentle as a tide. The preservation of these traces and of the body fossils themselves is itself a story worth pausing over, because the organisms of the Ediacaran should not, by any normal geological logic, have survived in the rock at all. They were soft. They had no shells, no bones, no hard mineralized structures to resist decay and time. A modern soft-bodied animal dying on the seafloor today would be consumed by bacteria and scavengers within days or weeks, leaving nothing, or almost nothing, in the sediment. The chance of a large, soft, thin organism like Dickinsonia making it through 600 million years of burial and heat and pressure and time to emerge intact in a piece of sandstone is, by any ordinary calculation, vanishingly small. And yet here they are, preserved in extraordinary detail, not just their outlines but the individual ribs, the midline, the glide reflection pattern of the isomers, the subtle differences between one end and the other that tell us which end was the growth pole and which was older. The reason they survived, and the reason they are so legible, is the mats. The same thick microbial carpets that fed them in life also preserved them in death, or rather, the chemistry of those mats created conditions in which a particular kind of preservation was possible that would not occur on a bare, uncolonized seafloor. The process is sometimes called Ediacara style preservation, and sometimes described with the almost poetic phrase death masks. When a Dickinsonia or a Charnwood died and settled into the mat itself, dense with microbial life, chemically reactive, rich in sulfur-processing bacteria, responded to the decaying body by precipitating minerals. Pyrite, iron sulfide, the mineral we sometimes call fool's gold, formed in thin sheets at the boundary between the decaying organism and the sediment. Casting the body's shape in metal as it dissolved, the body itself disappeared. But its shape remained, printed in chemistry into the layer of stone just above the mat, a film of mineral exactly matching the organism's contours, held there as sediment slowly accumulated above and around it, and time compressed everything into rock. It is a remarkable collaboration between biology and geology. The mat made the mould, the chemistry of decay made the cast, and 600 million years of slow, patient burial made it permanent. Without the mats, we would have almost nothing of the Ediacaran garden. With them, we have 200 genera of organisms preserved in sandstones on 6 continents, telling us the shape of a world we could otherwise not have imagined. 200 genera. The number deserves a moment of quiet. These were not a handful of isolated curiosities. This was a biosphere, diverse, widespread, presumably ecologically complex in ways we are still working out, covering the seafloor of ancient oceans, from what is now Australia to what is now Russia, to what is now Newfoundland, to what is now Namibia. A world of organisms, all soft, all mouthless, all apparently peaceful, distributed across the global ocean floor in communities that varied by depth and by time and by whatever local conditions shaped them. Among the most architecturally strange of these, and the competition for that title is intense, are the rangeomorphs. Rangia and Fractofusus and their relatives are organisms that have, in the view of most researchers who study them, no direct living descendants. No modern animal or plant or fungus shares their basic design. They were built on a principle that mathematicians call self-similarity or fractal branching, the same structural pattern repeated at multiple scales. The way a coastline looks similar whether you view it from a satellite or from a cliff or from a rock pool at its edge. A rangeomorph would branch into smaller branches, each of which would branch in the same way into still smaller branches, each of those branching again, the pattern repeating perhaps 4 or 5 times from the main stem to the finest visible division. The result was a surface area that was, for the organism's size, extraordinarily large, a body that was mostly edge, mostly surface, mostly boundary between the organism and the water around it. And that, most paleontologists believe, is exactly the point. An organism feeding by osmotrophy, absorbing nutrients across its body surface, is in direct competition with itself. Its own interior is wasted space, and only the surfaces that touch the water can do the work of feeding. Fractal branching solves this problem with a kind of mathematical elegance. It packs the maximum possible surface into the minimum possible volume. A rangeomorph was, in a sense, a surface area maximization machine, an organism whose entire form was shaped by the logic of absorptive feeding, the way a cactus's entire form is shaped by the logic of water conservation in an arid landscape. The architecture is the diet, made visible. The fractal branching of rangeomorphs was not haphazard. It was regular, consistent enough that it can be measured and modelled and compared across specimens and found to follow the same rules from one organism to another, self-similar in the technical sense, the branching ratio and the angle of each division maintained with a fidelity that implies something like a genetic program, a developmental code generating the same pattern reliably across a population. The fact that this code existed, that organisms in the Ediacaran already had the machinery to build complex, repeating, three-dimensional structures according to precise rules, is itself remarkable evidence of just how far multicellular life had already come by this point in the story. Even without a mouth, even without an eye, or a limb, or a gut. At Mistaken Point, on the eastern tip of the island of Newfoundland in Canada, an entire community of rangeomorphs is preserved in a single bedding surface, lying exactly where they lived, exactly as they fell, frozen in place by a layer of fine volcanic ash that settled through the water column approximately 565 million years ago and buried them before anything could disturb their arrangement. The site is a UNESCO World Heritage Site now, and it deserves the designation. It is sometimes called the Precambrian Pompeii, the same logic, the same terrible, accidental gift of catastrophe. A community caught in mid-existence by a geological event that should have destroyed them, but instead preserved them. Because the ash settled gently enough and quickly enough to cast each organism in place before the seafloor microbes could begin their work. Walk the surface at Mistaken Point if you ever find yourself on that windswept Newfoundland coast, and you will see dozens of these organisms in a single field of view. Frond-shaped forms, disc-shaped forms, elongated spindle shapes, all distributed across the stone in the positions they occupied on the living seafloor more than 500 million years ago. The community is intact, not a collection of isolated specimens, but an actual community, a snapshot of how these organisms arranged themselves in space, who grew near whom, what densities they achieved, what the living garden actually looked like from above. And that spatial information has been used in the decades since Mistaken Point was recognized as the extraordinary site it is, to answer questions that go beyond simple description. A study published in 2015 by Mitchell and colleagues looked at the spacing patterns of Fractofusus populations preserved at the site and found something that would have seemed, to someone without the context, almost impossibly domestic. The distribution of Fractofusus specimens across the bedding surface was not random. It was clustered in a specific way, with large individuals scattered at intervals and smaller individuals clustered around them in patterns consistent with what you would expect from vegetative reproduction by stolons. Runners, the Fractofusus population at Mistaken Point appears to have propagated itself the way strawberry plants do. The original, larger individual sending out horizontal extensions, each of which established a new individual nearby, which then sent out its own extensions, building up a local cluster of related organisms around each founding parent. It is a strange thing to sit with, this image. An ancient seafloor, 565 million years ago, deep in the cold water of a neoproterozoic ocean. covered in organisms that spread themselves across the sediment by sending out runners the way a strawberry plant covers a garden bed, quietly, slowly, patient and purposeful in the way that only something without a nervous system can be patient. The community growing not by pursuit or competition, but by extension, each individual reaching out, establishing a daughter which reached out in turn, a garden reproducing like a garden. Fractofusus is not alone in its strangeness. Among the Ediacaran organisms that we know from multiple sites and multiple continents, there are forms that challenge almost every intuition about what an animal should look like. Tribrachidium is one. It was a small, roughly circular organism a few centimeters across, that bore 3 curved ridges arranged around a central point, like the blades of a fan, or like the Triskelion symbol that appears on certain ancient coins. 3-fold rotational symmetry, not bilateral, like a fish or a worm or a human, where the left side mirrors the right. Not radial, like a jellyfish or a sea anemone, where any number of arms radiate out from a center. 3-fold. A symmetry that almost no living animal uses, though it appears in some developmental stages of echinoderms, the starfish and their relatives, and in certain rare abnormalities in the growth of otherwise bilateral organisms. What Tribrachidium ate, or how it fed, or how it reproduced, we do not know with confidence. The 3-fold symmetry does not correspond to any known feeding apparatus. There is no obvious structure that resolves into a mouth or an intake, no groove or pore that paleontologists have identified as an opening. Like so many Ediacaran organisms, it sits in the sediment and presents its shape to us with complete indifference to our need for explanation. It was here. It was successful enough to leave specimens in multiple locations. It had a body plan that evolution generated and maintained, and eventually abandoned without bequeathing it to anything we can identify as a descendant. That is all we can say with confidence, and it is, in its own way, enough. It is a reminder that the space of possible body plans is larger than the selection of plans that survived. Sprigina is another. Named for Reg Sprigg himself, the geologist who first found the Australian fossils in 1946, whose report was doubted and whose organisms were dismissed as curiosities for years before the field caught up to what he had actually found. Sprigina is a small, segmented form, roughly centimetre scale, with a differentiated head shield and a body of repeated units. It was, for a time, compared to the ancestors of trilobites, those hard-shelled Cambrian arthropods that would come to dominate the seafloor not long after the Ediacaran ended. The comparison is now regarded with caution. Sprigina may or may not be related to any Cambrian lineage. The segmentation may reflect convergent evolution rather than shared ancestry. But it is striking, even in uncertainty, as an example of bilateral symmetry, of differentiation along a body axis, a front and a back, a head end and a tail end that suggests something of what was coming. A preview in soft tissue of a design that would, in harder, more armoured form, eventually transform the seafloor. And then there is Parvancorina, another small Australian form, shield-shaped and ribbed, with a raised central ridge and what appear to be lateral ridges branching from it, a structure that has been variously interpreted as the precursor to an arthropod-like body plan, as a filter-feeding structure, as something else entirely. Parvancorina specimens have been found oriented in specific directions relative to ancient current indicators in the rock, which suggests that these organisms may have positioned themselves to catch whatever the current carried, a behavior, a response to the environment, however simple and slow and chemical it may have been. Aspidella is simpler still. disc-shaped, sometimes showing concentric rings, preserved in large numbers in certain Ediacaran formations, Aspidella was for many years interpreted as a holdfast, the base that anchored a frond-shaped organism to the sediment, the equivalent of a root, a disc of tissue that gripped the mat while the rest of the organism lifted into the water above. Many specimens of Aspidella show no attached stalk or frond, which led to some confusion about what exactly had been found, but the holdfast interpretation, for at least some of them, is well supported. These were the anchors of the garden. The fixed points from which frond-shaped organisms, Charnwood and its relatives, rose into the water column, held in place by the disc below, while the frond above spread its fractal surfaces into the current and whatever dissolved nutrients the current carried. To stand in this garden, in your imagination, and see it whole, the mat-covered floor. The disc-shaped holdfasts, the fronds rising from them in gently drifting rows, the flat-ribbed ovals of Dickinsonia and Ilya moving almost imperceptibly across the mat surface, the small three-armed rosettes of Tribrachidium, the clustered runners of Fractophusus spreading outward from their parent forms, is to understand something that the summary descriptions of Ediacaran life often miss. This was not a barren or a minimal world. It was rich. It was architecturally varied. It was ecologically structured in ways that would require considerable effort to reconstruct fully, and the reconstruction is still very much in progress. But it was organized. It had guilds, probably, organisms that occupied different roles, different depths in the water column, different relationships to the mat, different reproductive strategies. It was a biosphere, not an accident. And it was, from a certain point of view, extraordinarily stable. The Ediacaran period spanned roughly 635 to 538.8 million years ago, nearly 100 million years. Within that long span, the fossil record does not show the rapid, repeated overturning of ecological structure that characterizes later periods of Earth history. The garden, once established, persisted. Its dominant organisms remained dominant, in broad terms, for tens of millions of years. Compare this to the Cambrian, which followed immediately after and produced an almost bewildering proliferation of new body plans in something that looks, by geological standards, like a geological instant, and the contrast is instructive. The Ediacaran world was not a world in transition. It was a world that had found a way to exist and was, in the absence of anything to disturb it, content to continue. The three assemblages that paleontologists have identified within the Ediacaran represent not sudden breaks but slow, overlapping shifts in which kinds of organisms dominate the record. The oldest is the Avalon assemblage, dated to roughly 575 to 560 million years ago, and it is characterized by deep-water, ranger-morph-dominated communities, the kind preserved at Mistaken Point. These organisms lived in the dark, below the sunlit zone, in cold, quiet water, far from the shallow seafloors that most people imagine when they think of ancient marine ecosystems. The Avalon assemblage is important partly because it represents the first large, complex, macroscopic body fossils in the rock record, the Avalon explosion, as it is sometimes called, a burst of ecological complexity that predates the famous Cambrian explosion by some 75 million years and challenges the old narrative in which complex life simply appeared, abruptly and mysteriously, at the base of the Cambrian. Something was already happening long before the Cambrian. Something had already found a way to build large, architecturally complex bodies and distribute them across the global ocean floor. The Cambrian did not invent complexity, it reinvented it with different tools. The White Sea assemblage roughly 560 to 550 million years ago, represents a somewhat shallower, more diverse community. The world that includes Dickinsonia, Cambrian, Yorgia, and many of the best-known Ediacaran organisms. The White Sea coast of Russia, with its cliffs of pale Ediacaran sandstone at sites like Lyamtsa and Zimny Gori, has produced some of the most extraordinary specimens in the record, large, well-preserved Dickinsonia with their glide reflection symmetry intact, the resting traces we have already considered, and the organic films that would, in 2018, yield something no one who studied these fossils in the preceding century could quite have imagined possible. The Nama assemblage, the youngest, from roughly 550 to 539 million years ago, named for the Nama group in Namibia, represents the final chapter of the garden, and it is in some ways the most quietly ominous. Not because of what it contains, but because of what it begins to contain that the earlier assemblages did not. We will return to that. There is still more of the earlier world to understand before we reach the ending. Approximately 580 million years ago, that is, roughly 45 million years into the Ediacaran, and still some 40 million years before the period's end, the Earth experienced a second glaciation. It is known as the Gasquias glaciation, and it was a brief event by geological standards, probably lasting less than 1 million years, and it was not as severe as the Marinoan snowball Earth that had preceded the Ediacaran's opening. But it was real, and it was global, and it left its own layer in the rock record. And it occurred very close in time to the Avalon explosion, that first burst of large, complex Ediacaran life. The relationship between the two events is not fully understood. Some researchers have suggested that the glaciation, by disrupting nutrient cycles or altering ocean chemistry, may have triggered or accelerated the evolutionary innovations that produced the Avalon assemblage. Others are more cautious. The timing may be coincidental, or the causal relationship may run in a direction we have not yet correctly identified. This is one of many places in the Ediacaran story where honest uncertainty is the most accurate position. What is somewhat clearer is the role of oxygen. The Ediacaran coincides with, and in some ways was made possible by, what geochemists call the Neoproterozoic oxygenation event. A rise in atmospheric and oceanic oxygen levels that accompanied the end of the snowball Earth glaciations and continued through the Ediacaran and into the Cambrian. Oxygen matters enormously for complex, multicellular life. A single-celled organism can survive on very low oxygen levels because the diffusion distance between its surface and its interior is so small that oxygen can reach the center of the cell without a circulatory system to carry it. A large, multicellular organism cannot. The more cells you have, the more oxygen they collectively need, and the more difficult it becomes to distribute that oxygen throughout the body without a dedicated transport system. The rise in oxygen during the Ediacaran was, in a sense, the unlocking of a constraint, a raising of the ceiling on how large and how complex a soft-bodied organism could become and still keep every cell supplied with the oxygen it needed to stay alive. This is not to say that oxygen simply caused the Ediacaran biota. The relationship between rising oxygen and the appearance of complex life is not a simple switch. It is more like a slowly opening door, the chemistry of the ocean changing over millions of years in ways that made new things possible, and the organisms of the garden taking advantage of those new possibilities in the ways that their existing biology allowed. The fractal branching of ranger morphs, the flat, absorptive surfaces of Dickinsonia, the anchored fronds of Charnwood discus, all of these designs are more viable in a more oxygenated world than they would have been in the oxygen-poor oceans of the early Proterozoic. The world changed, and life changed with it. Not in a single dramatic moment, but in the long, slow way that geology changes everything. There is a hypothesis, influential, contested, and worth knowing, that attempts to describe the fundamental nature of these organisms in a way that sets them apart from all subsequent life. It was proposed by the German paleontologist Adolf Seelacher, one of the most original minds in the field, who spent decades developing a framework for understanding trace fossils and body plans that revolutionized several corners of paleontology. Seelacher proposed that many Ediacaran forms belonged to a group he called the Vendobionta, and his central claim was that they were not animals. Not fungi, not algae, but something else entirely. A separate experiment in multicellular life, a different way of being large and complex that evolution generated once and then, when the Cambrian came, abandoned without issue. The key feature of the Vendobionta, in Seelacher's view, was their construction from fluid-filled or gel-filled compartments, sealed quilted units, each self-contained, assembled together like an air mattress or a waterbed into the larger body form. He called these units pneus, from the Greek word for breath or air, and he argued that the ribbed patterns we see in Dickinsonia, the fractal chambers of rangomorphs, the multi-part construction of pteridinium and Ernietta from the Nama assemblage, all reflected this fundamental building principle. Each compartment was, in this view, largely independent. It did not exchange fluids or signals with its neighbours in the way that the cells of a true animal body communicate and cooperate. The organism was a collective of sealed units, not an integrated body. The Vendobionta hypothesis has not been universally accepted. Many researchers who work on Ediacaran organisms argue that at least some of these forms, Dickinsonia most prominently, following the 2018 cholesterol evidence, are genuine animals, and that the quilted construction is a convergent feature arising from the constraints of osmotrophic feeding, rather than evidence of a separate biological kingdom. The debate is real and ongoing, and it reflects genuine uncertainty about organisms that have left us only their shapes, without the molecular or cellular information that would resolve the question definitively for most of the 200 genera involved. But Seelacher's hypothesis, even where it is contested, is valuable for what it forces us to consider. The possibility that the Ediacaran garden was not simply an early, incomplete draft of the world we know today, but something genuinely different in its biological logic. A different answer to the problem of being large and multicellular. An answer that worked, for a very long time, on its own terms, and that may have represented a road not taken. A possibility opened up by the post-snowball oxygen surge, and then, eventually, closed again when the road that led to mouths and guts and teeth proved, in evolutionary terms, to be more productive. Pteridinium and Ernietta. The Nama assemblage, forms that Seelacher most strongly associated with the Vendobionta, are worth pausing on briefly for their own sake, because they are striking organisms even by the standards of a period that is not short of striking organisms. Pteridinium was large, up to 30 centimetres and more, and it was frond-shaped, like Charnia. But its construction was different, 3 vein-like panels of ribbed tissue, assembled around a central axis, each panel bearing the quilted architecture that Seelacher found so significant. Some specimens appear to have been largely buried in the sediment, with only a small portion of the organism extending into the water above. Others seem to have lain flat on the sediment surface. Exactly how pteridinium oriented itself in life, and exactly what it was doing with its three veins, remains a matter of active interpretation. But it is, in any photograph, unmistakably strange, a three-winged form built on a plan that has no living equivalent and that appears and disappears entirely within the Ediacaran, leaving nothing behind it in the Cambrian record that can be recognized as its descendant. Ernietta was different again, roughly sack-shaped, with a quilted exterior partially buried in the sediment, and found in some localities in dense aggregations that may indicate gregarious growth, possibly related to reproduction or to some shared chemical environment in the sediment. Its shape suggests, to some researchers, that it may have been filtering water that flowed over and around it, or absorbing nutrients from the sediment in which it was partly buried. To others, it remains simply a form whose biology is not yet readable in the detail we would like. This is the honest state of knowledge about the Ediacaran garden. We can describe the shapes with great precision. The technology of modern paleontology, from three-dimensional scanning to geochemical analysis to spatial statistics, has given us a level of physical detail about these fossils that would have astonished the scientists who first described them. But the biology, the mechanisms, the metabolisms, the ecological relationships, the reproductive strategies, the responses to environmental change remains partly in shadow. We can read the shapes of the organisms in the stone. We are still learning to read the lives behind the shapes. And yet, what we can read is enough to say, with confidence, that this was a world of genuine complexity and genuine diversity. Not the barren pre-Cambrian ocean that an older generation of geologists assumed had to have existed, featureless, microbe-dominated, waiting for the Cambrian to arrive and make it interesting. A world of its own, with its own architecture, its own ecology, its own quiet strategies for existing, for growing, for persisting across tens of millions of years of changing ocean chemistry and periodic glaciation and the slow accumulation of oxygen in the water and the air. A garden, in the metaphor that Mark McMenamin gave to it, and like any garden that has existed long enough. Varied and strange and full of forms that do not map neatly onto anything in the world we know. The quiet of that ancient seafloor was not the quiet of absence. It was the quiet of a world that had simply not yet learned certain things. It did not know about speed or hunger or the strategies of pursuit and evasion. It did not know about hard surfaces, the shells and plates and mineralized teeth that would come later, first hinted at and then fully realized in the Cambrian record. The architectural revolution that would give predators the tools of their trade and give prey the armor to survive them. In the Ediacaran, none of this had happened yet. The chemistry of life had not yet crossed the threshold that makes biting possible, or fleeing necessary, or anything more urgent than the slow absorption of nutrients across a soft surface pressed against the mat. But the threshold was approaching. Slowly, at the pace at which geological thresholds approach, which is to say, invisibly from any single moment's perspective, but unmistakably in the record of the stone. In the Nama assemblage, the youngest of the three worlds within the Ediacaran, something was already beginning to change, something that would, within a geological eye blink, remake the seafloor more thoroughly than anything since the mats themselves had first spread across it. We are not there yet. The garden still holds, the mat is still thick. The ribbed forms of Dickinsonia still rest against it in the Ediacaran silence, their edges in contact with the microbial film. Their impossibly thin bodies spread wide to absorb whatever the quiet chemistry of that ancient ocean offers them. The fronds of Charnwood still lift from their aspidella holdfasts and reach into the current. The Fractifusus colonies still spread their runners outward from each parent organism, building their local clusters across the sediment surface. Patient and methodical and entirely indifferent to the changes accumulating slowly in the chemistry of the water above them. And yet something was changing in the chemistry of the ancient ocean and in the bodies of the organisms that lived within it, and the record of the stone holds the evidence of that change with a patience and a precision that took the better part of a century for science to develop the tools to read. The question that had haunted Ediacaran paleontology since the beginning, since Reg Sprigg had first lifted those impressions from the red sandstone of the Ediacara hills, since Roger Mason had carried the traced outline of Charnia Masoni down from Charnwood Forest and handed it to his geology teacher, was a question so fundamental that without an answer to it, everything else about this world remained provisional. Everything else about the nature of the garden, the biology of its inhabitants, the meaning of the record they had left behind, hung from a thread that nobody had yet managed to pull tight. The question was simply this: what were they really? Were they animals? Were they related to anything alive today? Or were they something else entirely? A kingdom of life that flourished and vanished without descendants, without analogues, without any surviving lineage that could be traced forward through geological time to a living form that a biologist could hold in a jar and study and compare. Adolf Seelacher had suggested exactly this possibility with his Vendobionta hypothesis, and while the idea was contested, it could not simply be dismissed, because the fossils themselves, for all their extraordinary detail of shape and surface texture, could not answer the chemical question. A shape pressed into sandstone tells you how something was built. It does not tell you what it was made of. And in biology, what something is made of is often the most important fact of all. The shapes of Dickinsonia had been studied for decades. The glide reflection symmetry of its ribs had been measured and documented. The growth pattern, new modules added at one pole, the organism lengthening through its life in a sequence that could be followed specimen by specimen from the millimetre-scale juveniles to the great flat mats more than a metre long, had been worked out with care. The resting traces and the consumed patches of microbial mat attributed to Dickinsonia and to the related Yorgia had been identified and described and argued over. All of this constituted a remarkable picture of an organism's biology. But the central question, animal, fungus, lichen, or something with no name, something that had never survived into a world where it could be dissected and chemically analysed, remained unanswered. Then, in 2018, Ilya Bobrovskiy and Jochen and their colleagues at the Australian National University published a paper in the journal Science that changed the picture in a way that could not easily be argued away. What they had done was not, in principle, complicated. What it required in practice was a combination of extraordinary access, painstaking technique, and the kind of geological fortune that only very patient science occasionally encounters. The specimens they worked with came from the White Sea coast of Russia, from the same cold and remote cliffs that had yielded so many of the richest Ediacaran impressions, the strata of Liamsa and Zimny Gori, where Dickinsonia individuals of remarkable size and preservation had been documented for years. What Bobrovskiy and his colleagues understood was that some of these specimens preserved something more than a shape. Between the fossil and the surrounding rock, in the thinnest imaginable film of organic residue, a ghostly brown smear no thicker than a coat of paint. Something of the organism's actual chemistry had survived. Not its cells, not its proteins, Those had degraded long ago, dissolved back into the chemistry of the deep geological past. But certain molecules, the most durable of organic compounds, had endured 558 million years of burial and pressure and slow chemical transformation, and still retained enough of their original structure to be recognized with the right instruments for what they were. Those molecules were cholesteroids. Cholesterol is a molecule that your body makes and depends on. It is a fat, or more precisely, a sterol, a particular kind of lipid, and it is present in the membranes of every cell in your body in quantities so large that the word seems almost inadequate. Your brain is made largely of cholesterol. The membrane of every neuron that carries the signal of your thoughts depends on its presence. When scientists talk about cholesterol in the context of diet and health, they are talking about a molecule so fundamental to animal life that virtually every animal on Earth makes it in abundance. Bacteria do not make cholesterol in this form. Algae make different sterols, related molecules, but with distinct structures that can be distinguished by the same instruments that paleochemists use to read ancient rocks. Fungi make their own variant, ergosterol, again chemically distinct. The particular form of cholesterol that animals produce, and the particular degraded form, cholestane, and its relatives, that it becomes over millions of years of geological transformation, is a chemical signature that belongs with very high specificity to animals, and it was this signature, the fossil form of cholesterol, the molecular ghost of the same fat that builds your cell membranes, that Bobrovskiy and Brox found in the organic film preserved on the White Sea Dickinsonia specimens, dominated by cholesteroids, rich with them in a ratio and a form that left very little interpretive room. This was not a bacterial signal. It was not an algal signal. It was the chemical flag of an animal. The debate that had run for decades, animal, fungus, protist, vendobiont, member of a lost kingdom, was not ended cleanly, because science rarely ends debates cleanly, and because the interpretation of ancient biomarkers always carries some residual uncertainty. But the paper represented the strongest direct chemical evidence that had ever been brought to bear on the question. And the conclusion it supported was the conclusion that many paleontologists had long suspected but had never been able to prove at the molecular level. Dickinsonia was a true animal, a metazoan, one of the oldest confirmed animals in the fossil record. At roughly 558 million years old, its animality written not in its shape, which had always been ambiguous, but in the fat preserved in the stone, the fat that is the same, in its fundamental chemistry, as the fat in the membranes of the cells of the person lying here now, in the quiet, listening to this. There is something in that fact that takes a moment to settle. A molecule that runs through your own body, altered by 500 million years of geological time, but still recognizable, still structurally legible to the instruments of modern chemistry, was the key that finally turned in the lock. The garden was not merely an abstract geological mystery, not a parade of shapes in stone that could be debated in taxonomic abstraction forever. It was a world of animals, real animals, built from cells that made the same fundamental fats that animal cells make today. The quilted mat, the ribbed oval that slid across the microbial carpet of the Ediacaran seafloor, absorbing its meals through the whole surface of its impossibly thin body. That was an animal. The oldest animal many of us will ever encounter in any form. Its cholesterol, pressed into sandstone on the White Sea coast of Russia, is the evidence. And knowing that Dickinsonia was an animal, knowing it with the specificity that chemistry, rather than morphology, allows, changes how you think about everything else the garden contained. Because if Dickinsonia was an animal, and the biomarker evidence says it was, then the whole question of what these organisms were doing on the Ediacaran seafloor, how they fitted into something we might call an ecology, becomes more concrete and more answerable. They were not a separate, failed experiment in multicellular life that left no descendants and obeyed no rules of animal biology. They were animals, and they were there, living in the garden, absorbing the mats, growing by the slow addition of modules, reproducing in the still and silent water of a world that had not yet discovered the terrible efficiency of a mouth, which makes what came next, even at the very edges of the Ediacaran, feel like the beginning of something irreversible. The first sign appeared not in the shape of any organism, but in the behaviour implied by a trace. Cambrian, known from the White Sea assemblage at roughly 555 million years ago, looked different from the rangemorphs and from Dickinsonia. It was mobile in a more purposeful way, and the sediment around Cambrian specimens preserved something that the sediment around most Ediacaran organisms never shows: scratch marks. Fine, parallel grooves in the microbial mat, radiating outward from the resting positions of Cambrian individuals, in patterns consistent with a repeated, directed action. The interpretation, debated, as all interpretations in Ediacaran paleontology are debated, but supported by careful analysis of the spatial relationships between the organism and its traces, is that Cambrian was equipped with something functionally similar to a radula. A radula is the rasping, ribbon-like feeding organ that modern mollusks, snails, slugs, chitons use to scrape algae and organic films from surfaces. It is not a jaw, it is not teeth in the vertebrate sense, but it is a hard, directed, purposeful structure for harvesting food by actively removing it from a substrate rather than simply absorbing whatever diffuses across a passive surface. If the interpretation of Cambrian's scratch marks is correct, and it remains an interpretation, the leading one, but contested, then Cambrian was the first hint in the fossil record of something that would define every ecology that came after it. Not quite predation. Not quite grazing, in the sense that a modern herbivore grazes. But active feeding. Directed acquisition of food by an organism that moved to the food and then used a structure to harvest it. The first appetite, or something very close to it, leaving its marks in the stone of the White Sea assemblage 555 million years ago. The garden was still peaceful. There was no chase, there was no pursuit, no evasion, no animal fleeing from another animal that wanted to consume it. Cambrian's scratch marks represent something more like a grazing that a living lawn might experience from a very slow and gentle lawnmower. The mat scraped, the Cambrian organism moving on, the mat growing back behind it, the whole interaction too low energy and too slow to constitute anything that would register as danger. But the principle was there. The principle of directed, purposeful physical harvesting of food, the principle that, given enough time and enough evolutionary pressure, would develop into jaws and into teeth and into the predatory ecology that defines almost every complex environment on Earth today. And then, in the Nama assemblage, at the youngest edge of the Ediacaran, in the rocks of Namibia. In the Nama group, where some of the last Ediacaran communities left their impressions before the Cambrian boundary closes over the whole record, something else appeared. Something that would have been unthinkable in the Avalon Deep unimaginable even in the white sea world of Dickinsonia and Cambrian. Something that marks, as precisely as any line can be drawn in a record this old and this complex, the moment when the garden began to end. Hard shells. Claudina was a tube, small, calcareous, nested inside itself in a way that suggests it was built by an organism adding new material at one end as it grew, the way certain modern worms build their tubes, the way coral polyps secrete their cups. It was not large. Its tubes, found in the Nama Group rocks of Namibia and in equivalent strata elsewhere around the world, are sometimes only a few millimeters in diameter. But it was the first organism in the entire history of life on Earth, or the first that we can document in the fossil record, to have built a hard external structure from calcium carbonate, to have pulled calcium and carbon out of the surrounding seawater and used the chemistry of its own body to precipitate a mineral shell around itself. And alongside Claudina in the Nama assemblage, Namacalathus built calcareous cups of its own, goblet-shaped structures fixed to the seafloor, suggesting that biomineralization, the biological manufacture of hard, mineralized tissues, had arrived not as a single invention, but as something that multiple lineages were discovering or converging upon at roughly the same time. Why would an organism build a shell? The question has an obvious answer once you are living in a world where something else might eat you. A shell is armor. It is the body's response to the existence of a predator, a mineralized barrier between the soft tissues inside and the hard or sharp structures outside that might otherwise break through to them. In the modern ocean, shells exist because jaws and teeth and claws and drill bits exist. The two sides of the arms race are inseparable. The shell implies the threat that made it necessary, and the threat implies the shell that forced it to develop tools sharp enough to breach it. And that is why the boreholes in Claudina tubes are so significant. Among the Claudina specimens recovered from the Nama group, some bear small round holes drilled through the calcareous wall. The holes are too regular, too consistently sized and positioned to be accidents of preservation or weathering. They are interpreted, and the interpretation has held up under repeated examination, as evidence of predation. An organism, unknown to the fossil record, drilled through the shell of Claudina to reach the soft body inside. The predator itself left no trace we can read, but its action is preserved in the hole it made and in the pattern of holes across the Claudina specimens, a pattern that shows selectivity, that shows the holes are not random, but are placed where a soft tissue would have been accessible. Something drilled through the first shell in the fossil record, and it drilled with what appears to have been purpose and skill. The art of predation, the directed, persistent, patient work of breaking through another organism's defences to consume what lies within, was already being practiced before the Cambrian boundary arrived. The garden was ending. Not quickly. Not in any way that any single Dickinsonia sliding slowly across the mat, or any Charnwood lifting its frond into the current from its holdfast disc, would have experienced or registered. The ending was geological, imperceptibly slow in any individual lifetime, unmistakably clear in the rock record that accumulated across tens of millions of years. But it was ending. The soft, mouthless, predator-free world of the early and middle Ediacaran was giving way to something harder, more competitive, more dangerous. Something that would, in the geological eye blink of the Cambrian explosion, fill the ocean with forms that bore no resemblance to the garden's inhabitants, forms with eyes, with legs, with mouthparts, with mineralized teeth and claws and compound visual systems, and the whole apparatus of predation and evasion that defines the ecology of the world we live in now. Why? The question has no single clean answer, and any account of the Ediacaran's ending that offers one, that says simply the Cambrian animals arrived and ate everything, or that says a mass extinction wiped the garden clean, is giving you a story that is simpler and tidier than the evidence supports. What the evidence supports is a confluence of causes, each real, each documented in some form in the geological record, none of them sufficient alone to account for the transformation. All of them operating together across the final tens of millions of years of the Ediacaran in a way that changed not just what lived on the seafloor, but the rules under which anything could live there at all. The biotic replacement hypothesis, sometimes called the biological arms race interpretation, holds that the arrival of mobile, mouth-bearing, eventually hard-structured Cambrian animals was itself the primary cause of the garden's end. That the Ediacaran organisms, which had evolved in a world without predation and without competition from organisms capable of directed feeding, were simply outcompeted and consumed once those organisms appeared. There is truth in this. The Ediacaran forms were not equipped for a world with predators. Their bodies had no hard structures to deflect attack, no nervous systems fast enough to register and respond to pursuit, no behavioral repertoire beyond the slow movement and passive absorption that the peaceful mat world had required. In a world where something could bite, they could not bite back. In a world where something could chase, they could not run. But the arms race interpretation, taken alone, misses something important about the mechanism by which the garden actually collapsed. Because the Ediacaran organisms were not simply outcompeted in a direct contest between two ecologies. The rules of the game were changed at a more fundamental level. The mat itself was destroyed. The Cambrian substrate revolution is the name given to a transformation of the seafloor that accompanied, and in some interpretations drove, the collapse of the Ediacaran world. The thick microbial mat grounds that had carpeted the seafloor for hundreds of millions of years, the living skin of bacteria on which the whole Ediacaran ecology depended. The mat that Dickinsonia consumed and Ilya left its footprints in and Cambrian scraped at the edges of were destroyed not by predation on the mats themselves, but by the behaviour of the new burrowing animals of the Cambrian. When animals began to burrow through the sediment in significant numbers and at significant depths, something that the trace fossil record shows happening with increasing frequency and complexity as the Cambrian opens, they churned the upper layers of the seafloor into a state of constant disturbance. They mixed oxygen into sediments that had previously been stable and anoxic below a thin surface layer. They broke up the mat structure, disrupted the chemical gradients that allowed it to form and persist, undermined the physical integrity of the leathery bacterial skin that the Ediacarans had evolved to exploit. Without the mat, the feeding strategies of the Ediacaran world ceased to function. Osmotrophy depends on a concentrated, stable source of dissolved organic material. External digestion depends on a mat surface that holds still long enough to be processed. Rangeomorphic fractal branching, optimized to absorb nutrients from seawater percolating through a stable mat ground community, is optimized for a world that no longer exists once the mat has been turned over by burrowing animals. The garden was not simply invaded. Its foundation was destroyed. The ecological infrastructure that had supported hundreds of millions of years of soft, mouthless, sedentary life was dismantled from below by organisms whose burrowing activity was itself a form of ecological engineering, the first large-scale restructuring of a marine habitat by the organisms living within it. And alongside the biotic causes, The geochemical record carries hints of environmental shifts that may have contributed to the pressures on the Ediacaran biota during this period. Changes in ocean chemistry, in the concentrations of dissolved oxygen, in the carbon isotope ratios preserved in carbonate rocks, in the evidence for pulses of low oxygen or anoxic conditions in parts of the Ediacaran Ocean, suggest that the physical and chemical environment of the seafloor was not stable across this boundary. Some researchers have proposed that episodic anoxic events, periods when oxygen levels in bottom waters fell sharply, may have stressed or locally eliminated Ediacaran communities in ways that left them unable to recover once the conditions returned. The Neoproterozoic oxygenation event had raised oxygen levels enough to permit the larger, more complex bodies of the Ediacaran world. But oxygen levels in the ancient ocean were neither uniform nor stable, and the chemistry of the boundary interval shows a record of perturbation and change that makes a purely biotic explanation for the garden's end feel incomplete. Some researchers have proposed reading the end of the Ediacaran as a mass extinction event, a discrete, relatively rapid collapse of diversity that parallels, in its structure, if not its cause, the more famous mass extinctions of the Phanerozoic, the end Permian, the end Cretaceous, the great die-offs that punctuate the history of complex life. The argument has force. The Ediacaran organisms do disappear from the record abruptly, in geological terms, and the diversity of the Nama assemblage, already lower than the rich variety of the White Sea world, falls toward the Cambrian boundary in a pattern that looks, in some interpretations, like the kind of rapid diversity loss that mass extinction events produce. Whether the boundary at 530, 8.8 million years ago, the Ediacaran Cambrian boundary ratified by the International Union of Geological Sciences as a GSSP in its own right, should be counted among Earth's extinction events, is a question that remains genuinely open in the scientific literature. But perhaps the most honest and the most accurate way to understand what happened to the garden is not as a conquest and not as a catastrophe, but as a transformation so complete that it left no ecological space for the world that had preceded it. The rules changed. The rules of life on the seafloor changed in ways that were cumulative and irreversible, the arrival of directed feeding, then the arrival of hard structures, then the arrival of burrowing, then the arrival of the predator-prey dynamic with all the evolutionary pressure it generates, and the organisms that had evolved under the old rules, for whom the old rules had been the only rules that had ever existed, simply had no purchase in the new world. They were not adapted to compete in a world with jaws. They were not adapted to live on a seafloor without mats. They were the perfect product of a world that was ceasing to exist, and when that world was gone, they went with it. This is not quite the same as saying they failed. A world in which no living thing could bite another. A world that persisted for nearly 100 million years, that filled the ocean with hundreds of genera of complex, feeding, reproducing, dying organisms, that produced the first confirmed animals in the fossil record and the first documented movement of an animal across a sediment surface, and the first known reproduction by runners, and the first chemical evidence of the molecule that still constitutes the membrane of every cell in your body. That world did not fail. It existed. It was, by the measures available to it, a success. It lasted. The Ediacaran biota occupied its world for longer than the entire duration of the period from the first fish to the first human being. The garden was not a failed experiment. It was a complete one, a world entire in itself, subject to its own rules, organized around its own principles of nutrition and growth and reproduction and community. It simply had no defenses against the arrival of something that obeyed different principles entirely. And when those principles arrived, the principles of pursuit and capture and hard structure and burrowing and the whole restless, competitive, iterative evolutionary machine that the Cambrian would set in motion, the garden yielded without a struggle it had any evolutionary toolkit to make. The mat thinned. The soft bodies, unarmoured, untoothed, without anything resembling a flight response, ceased to leave their impressions in the sediment. By the time the Cambrian fauna are fully established in the record, by the time the Burgess Shale and the Chengjiang biota preserve their extraordinary pictures of a world with eyes and legs and jaws and the first mineralized teeth of the conodont animals, approaching from the Cambrian Ordovician boundary in the fullness of geological time, the garden exists only in the stone. Pressed into the red sandstone of the Ediacara hills, captured in the siltstone of the White Sea cliffs, frozen in the volcanic ash of Mistaken Point, preserved in the Nama Group rocks of Namibia, where the last shells and the first boreholes mark the moment when the Old World and the New World briefly occupied the same seafloor. And there they remain, 100 genera and more, pressed into the stone of 5 continents, their shapes preserved with a fidelity that took geologists most of the 20th century to learn to read, and that is still, in the 21st, yielding surprises. The cholesterol of Dickinsonia, surviving 558 million years to confirm what its shape had only suggested. The scratch marks of Kimberella recording the first appetite in its fine parallel grooves. The boreholes in Claudina recording the first predator in its small, precise circles of absence. All of it preserved, all of it still there, still readable, still capable of yielding, with the right instruments and the right questions, answers to questions that nobody knew to ask until science had developed the tools to ask them. What does it mean that this world existed? That for nearly 100 million years, the most complex life on Earth consisted of organisms that had no mouths, no teeth, no eyes, no fear? That the first animals, and they were animals, the chemistry is clear on this, the cholesterol trapped in the White Sea stone, is the evidence, lived in a world so peaceful that the very concept of predation had not yet entered the ecology of the ocean. That somewhere on the seafloor of the ancient sea, a metre-long quilted oval of living tissue slid slowly across a mat of microbes and absorbed its meal through its skin, and that this was, at that moment in the history of life on Earth, one of the most sophisticated and successful ways that any animal had yet found to exist? It means that the world we live in, the world of pursuit and competition and hard structure, and the eternal negotiation between predator and prey that underlies every ecosystem on Earth today, is not the only way the world could have been. It is the way the world became. But before it became this way, there was another way. There was the garden. There was the quiet mat. There was the slow, absorptive, sedentary, peaceful ecology of the Ediacaran seafloor, operating under its own logic, obeying its own rules, filling its world with complexity and diversity, and the first tentative experiments in what it means for a collection of cells to be, together, an animal. We found it by accident in abandoned mines, on a schoolboy's walk through an English forest. We proved it was real by pulling cholesterol from stone. We read its feeding behavior in the shadow prints it left on a microbial mat and its reproduction in the clustered spacing of a community buried under falling ash. It is more real now than it has ever been. more legible, more reconstructible. The garden is gone, has been gone for 538 million years, and yet it is not lost. It is in the stone, patient and precise and infinitely detailed, waiting for the next question that science has finally become capable of asking. The night is very quiet. The world outside is the Cambrian world, the world with teeth and eyes and the whole restless machinery of competition and survival that has been operating without pause for more than 500 million years. But somewhere in that world, in the museums where Dickinsonia casts lie under glass, in the cliffs of Mistaken Point, where the ranger morphs are still exactly where they fell, under the volcanic ash 565 million years ago, in the red sandstone of the Ediacara hills that Reg Sprigg turned over in 1946 and held up to the South Australian light, the garden persists. The soft bodies in the stone, the glide symmetric ribs, the fractal branches of the rangomorphs, the holdfast discs of aspidella, the mats, the quiet, the absence of every threat that has defined the history of life in all the eons since. If you are listening from somewhere in the world tonight, from a city or a countryside, from a northern winter or a southern summer, from wherever you find yourself lying in the small hours with the quiet pressing in around you, I would genuinely like to know. The comments are there, and I do read them. There is something fitting about a community of people scattered across a Cambrian world, finding their way, in the dark and the stillness of the night, back to the garden. Back to the world before teeth, back to the long, slow, mouthless quiet of the Ediacaran seafloor, where nothing pursued anything, and the only work of life was to press softly against the mat and absorb what the ancient ocean offered. There are more stories here of the same slow and careful kind, waiting for whenever you want them. The deep past is very large and very strange and almost entirely peaceful at this hour. You have done enough for one night. The questions can wait. The stone will keep its impressions until morning and beyond. 500 million years is long enough to establish that the stone is patient. Let the deep thoughts settle, and let yourself sink with them.